For second talk this morning, we have Professor Tony Pantev from University of Pennsylvania, and he will be speaking about Hodge atoms and their applications.
Thank you, Maxwell. All right, so yeah, I would like to continue the story that Lyubimil started. Yeah. Okay, so yeah, I want to continue the story that Lyubimil started and explain a little bit how these atoms arise, how they are classified, and how they give you obstructions to rationality. So as Lyubimil mentioned, this is joint work. It's a bunch of papers. So the atoms theories, papers Lyubimil, Maxim, and Tony Yu. And then there are some of the applications that Ron is going to talk about on Thursday, and hopefully I'll mention them. I'm not sure. Okay, so the plan is to introduce atoms, and that's based on some machinery, which is machinery non-commutative Hodge theory, and it's about these creatures called F bundles and the way they decompose. And then once I introduce the machinery, I'll talk about the concept of Hodge atom, how we define them, and what their properties are, and then show you how they can be used as obstructions. Okay, so strictly speaking, I don't need to talk about non-commutative Hodge structures, but since this is what the origin of the story is and what motivated the introduction of an atom, I want to mention them briefly to put things in context. So there is this linear algebraic data called non-commutative Hodge structure, rational and pure in this case. And it consists of a vector bundle over the line. The vector bundle is graded by even and odd parts. There is a local system of Q vector spaces contained in that vector bundle and generating it over the function line. And then there is a meromorphic flat connection, which has a pole of order at most 2 at the origin. And then there is some compatibility between this data. The local system is flat, and it's compatible with Stokes data if the connection has irregular singularity at 0. And then, so the intuition here, the heuristics is that this connection encodes some slightly nonlinear version of the Hodge filtration. And the compatibility with the Q structure is the compatibility of the Hodge filtration with the Q structure. And then there is a compositeness condition, which is this last condition, which says that if you glue, using the rational structure, if you glue the original vector bundle to its complex conjugate to obtain a vector bundle of Q1, then that bundle that you get is homomorphically trivial. So this data together gives you this notion of non-commutative Hodge structure, and this is what one observes on the cohomology of non-commutative spaces of categorical flavor. So if you have a smooth, compact linear category, then with cohomology, you get this type of structure.
Can you remind us what Stokes data is?
Yeah, so I won't talk about that, but I'll say it very quickly. So the meromorphic connection has a pole of order 2 potentially at 0. So it doesn't have a regular singularity. If you want to have a Riemann-Hilbert correspondence for these types of connections, and connect it with some kind of locally constant sheaves, you cannot. So there is no naive Riemann-Hilbert correspondence that will convert homomorphic connections, meromorphic connections with poles of order bigger than one and local systems. But there is a slight enhancement. So the problem is the Stokes phenomenon, which is that flat solutions to homomorphic connections with poles of order bigger than one are only convergent on sectors. So knowing what those sectors are and how the flat solutions change when you go from one sector to the next, so that's the Stokes data. So the transformation matrices that give you the wall crossing by going from one sector to the next are the Stokes matrices. And there is a way to encode that data actually in filtration. So there is an actual constructible sheet, not a local system anymore. The constructible sheet of sections, which looks like a sheet of flat sections equipped with the filtration on the boundary circle near the structure. And that filtration encodes exactly how these solutions, flat solutions, jump when we go from sector to sector. So that's the source. I mean, there is some pretty hot story there also, because these Stokes filtrations, the way they jump per false ones. So the condition is that these Stokes filtrations are defined over the rational. But I'm not going to go into the rational story at all. In fact, I just wanted to put the definition here. Yeah, so these creatures, they are what you get on the homology of smooth and compact non-commutative space. And this is actually conjectural in full generality, but in many cases, we know how to construct them and prove that they satisfy all those conditions. Usual pure core structures are special cases. The only difference or the only tweak you need to make is that you need to fold the grading of the usual core structures and only view them as the Z2 grade core structures. But once you do that and you try to rewrite it in this type of data, then everything works in exactly the same way, except that you get special connections. The connections get regular singularities. And then you get variations. So if you have families of categories or families of non-commutative spaces, then you get variations of non-commutative core structures. And that's encoded in extending the connection nabla to a connection with regular singularities in the variation parameters. And so here is the most important example for this talk. If you have a compact symplectic manifold of dimension 2D, then you get a one parameter variation of non-commutative core structures on its homology. So the vector bundle is just a trivial vector bundle with fiber the homology of the space, built as a Z2 graded vector space. Yeah, so it's a one parameter variation. So Q is the variation parameter and U is the additional parameter on the line that we call it the Gaussian variation. So now it looks like a vector bundle, say, on the line or a formal origins on the product of a disk or a function of a disk. And you have a connection which has, in the U variable, has a second order pole. And it's the connection with the row in the previous talk. And I didn't write how it looks like in the Q direction. You'll see the general formulas later on. But the thing that gives you the Koch filtration, so the way the connection looks in the U direction, is given by this formula. It has a second order pole. The coefficient in front of that pole is the quantum multiplication with the first term class of X. And the quantum multiplication depends on the parameter Q, which scales the symplectic form. And there is a first order pole in the Laurent tail, and it is just the grading operator. It's the operator that multiplies homology of degree K by K minus the order. And so this depends on the Gromf-Witten invariance. It depends on the symplectic structure, and the direction of the deformation is given by the symplectic structure. And these are the types of guys that we're going to be looking for, and that they'll give us, combined with the usual core structures, they'll give us the birational invariants later on. And there'll be more formulas like that. The most general formula, I'll write it. Okay, so the way the obstructions and the interesting geometric information is extracted from this, it's all guided by homological mirror symmetry. So even though we don't use homological mirror symmetry to do it, it's guided by that. And there is one lesson that we learned by thinking about homological mirror symmetry throughout the years, which is that non-commutative core structures really do generalize these geometries that appear on the two sides. The problem with them is that they're very difficult to work with. They're much more complicated than an ordinary core structure. Even though they're kind of linearly algebraic data, then there's much more freedom in them. So the goal in order to extract useful invariants from them is to find some computationally viable projections of shadow of these variations of non-commutative core structures, which is easy to manipulate. And so that, like 5 years ago, we came up with this notion of an F bundle, which is a shadow of the non-commutative core structure, and it's basically all you need. And so here is it as a concept. One feature of this theory, which is very awkward, is that, of course, the theory makes sense algebraically, makes sense formally, makes sense complex analytically, makes sense rigid analytically. But the quantum product itself, even though we can formally define it, we don't know that it has any convergence property in the complex analytic sense, and or algebraicity property. Yes. Now it's not. Now it's just an even connection. Very good.
Even degree.
Yeah. I mean, it's not a super connection. Degree zero connection. Okay. But yeah, so because you need to do geometry with these guys, you can't really work with them formally, even though normally in symplectic topology, in Floyd theory, people work with them for the nomic field, which is a formal object. But here you really need to be able to evaluate the points in the parameters. And so you need to do something about that. Complex analyticity is not known, so like a device that allows you to do that is to work non-Archimedean in a non-Archimedean setting and treat the coefficient field, for example, as a non-Archimedean norm field with a residue field. So it's an equal characteristic non-Archimedean norm field with a residue field of characteristic 0. And work with rigid analytic varieties and rigid analytic bundles over there. So that actually does, even though it's like an infinitesimal improvement on dealing with formal things, it turns out to be enough to the geometry. Okay, so what's an F bundle? It's very similar to what a non-commutative core structures was. It's a super manifold. It's a super vector bundle over the super manifold. Everything is analytic over this non-Archimedean field. Then you have a connection, even connection on that cross a germ of a disk. It's flat. It has at most a second order pole in the U variable at 0. And in the other directions, it has at most a first order pole in the U. So that's basically what the variation of non-commutative core structures was. Without the rational structure and without positive condition. So this is just a statement about Koch filtration, but there is a requirement here that everything is a rigid analytic over this medium. Now, once you get this data, this set bundle data, so it's just a bundle with connection on super manifold across a disk, you get a lot of residual structures. So you get the vector bundle on the manifold just by restricting at the origin of the disk. You get a U connection. So you get a one parameter family differential operators on B parameterized by D, and the symbol of those operators is not given by the identity as to a connection, but is given by U times. You get the Higgs field, which is just the value of the U connection in zero, and it is an integrable Higgs field. And you get an extra symmetry, an endomorphism super vector bundle. And that endomorphism is just the coefficient in front of U squared. That was the thing that was the quantum multiplication by the first class in the example of the symplectic manifold. So that coefficient is now endomorphism of the vector bundle. And by the flatness, it actually commutes with the other pieces. Commutes with the U connection in particular. Okay. Now, if you have one of these F bundles, then you can view the Higgs field as a map from the tangent bundle of the supermanifold to the endomorphisms of the vector. So it realizes all vector fields on B as a family of commuting endomorphisms of H0. And so we say that the vector, this F bundle is maximal at a point if there is a cyclic vector, if there is an even vector in the fiber at that point, such that the map from the tangent space at this point to the fiber of the vector bundle given by this commuting family of operators is an isomorphism. And we say that the F bundle is maximal everywhere if it's maximal at every point. So there is this notion of a F bundle, which is essentially the Koch filtration on a non-commutative Koch structure. And among all of those, there is maximal. There's something that are slightly bigger than maximal, which also appear technical reasons, but I'm not going to talk about them. But the maximal ones are really important ones because they identify the vector bundle with the tangent bundle. And if you have a maximal F bundle, then the tangent bundle of the manifold is identified with the subalgebra in the endomorphism algebra, H0, which is commutative. So you get an algebra structure in the tangent. And if you write down what that algebra structure is and its properties, it's exactly what the properties of an F manifold are as defined and studied by Hartlink and Manning. And this maximal F bundles give you a little bit of extra structure. You don't just get general F manifold, you get a general manifold equipped with a special vector field, an Euler vector field. And it is just the unique vector field that corresponds to the operator kappa. That extra symmetry coming from the second order. And the products with respect to the Frobenius product of this Euler vector field itself actually generate the Lie algebra vector field. So the Lie algebra vector fields on the circle actually acts. Now, the great thing about these F bundles is that they have a very robust structure. So there are many decomposition states that you can write about. So for instance, if you have a rigid point in B, then we have a decomposition theorem, which says that if you know how the fiber of H decomposes at one point across the origin of the circle into a sum of generalized eigenspaces for the operator kappa, then that induces a canonical decomposition of the whole F bundle. So the base splits into a product of bases. On each of the pieces of the base, there is a bundle with connection, which is a bundle, and everything is an external sum. Pull them back to the product, then you have. So once you have a decomposition of a fiber which is compatible with that symmetry kappa, then the whole picture splits, at least in neighborhood.
Say where the non-Archimedean aspect is used.
Here it's not used at all yet. It will be used later when we define the invariants, because we need to do some geometry and we can't work with formal spaces. Right, so this theorem, we proved it first in the formal case, but then we realized it's needed in the non-Archimedean case, and so in order to use Jean and Jack proved it. Okay, and the main example of an F bundle again comes from symplectic geometry. It's the A model F bundle. I am denoting it by Bx, Hx, and nabla x, which corresponds to the universal family of Fukaya categories for a compact symplectic manifold. So I promised you the formula, so let me just go over this very quickly. So if you have a compact symplectic manifold, and you take a symplectic form with integral periods on X. And by the way, all the applications of this picture that we have will be just for small projective manifold over complex numbers, and all the symplectic forms that we're going to take will be just given by the angle of class of one rational the subspace of rational ones. So if you have one of those forms, then we get for any curve class, for any degree 2 homology class, we get genus 0 ground with an invariance. They correspond to the images of some virtual class on the moduli space of genus 0 curves with n mark points in the homology class beta. And they can be packaged in a generating series, which counts the symplectic areas of the curves, and pairs these classes with homology classes on X. So here the capital deltas are just a graded basis of homology. The little t's are the dual variables, and you just get this generating series that pairs products of homology classes with this homology class that comes from the virtual fundamental class on the moduli.
If you look at the formula, it doesn't seem to be any information. Just took a basis, you vary.
No, I and beta is the ground with class.
Where?
I and beta.
Oh, I and beta.
I and beta is homology class on the n product of the variety, which is the image of the virtual fundamental class of the moduli of pseudo-homomorphic curves with n function. That's the information. Plus there is this weight, which is the symplectic area of the curve. This W is not our formula. But yeah, that's where the problem. And okay, so let's take K to be the QSO series, form of QSO series in one variable. We can take it to be the Novikov field over Q. And then you can define beta X. I'm saying it's a ball. It's actually not really a ball. It's some kind of qualities in this rigid analytic space corresponding to the cohomology over that field. And F0 actually, so if you choose your qualities carefully with the correct estimates, F0 is convergent. And so then you use the Poincare pairing, define the quantum product by using the third derivative of F0. And it actually satisfies all the properties, all the axioms you need for a product. And take the trivial vector bundle with fiber homologies. And then you can write the A model bundle. So these are the complete formulas. So it lives over this polydisk in the cohomology cross one-dimensional formal disk with variable u. In the u direction, it is given by a Laurent tail that has two terms. One is the grading operator that we had before in degree -1. In degree -2, you have a multiplication by an operator. So this is the operator. It's multiplication by minus the first-chain class plus the sum of all the homology classes. In fact, only homology classes of degree not equal to 2 appear in that extra sum because you subtract it there. And quantum multiplication by that. So if you specialize that to the one parameter deformation, which just goes in the direction of the single symplectic form, you get the formula that I had before. These extra variables disappear because all the T alphas are 0. But you really need the whole thing. So that's the A model F bundle. It depends on the Gronk-Witten theory, and it depends on all integral symplectic forms. The space of all symplectic forms. These are the deformation parameters for the variation. And as I said, on a projective manifold, we'll just take the Néron-Severi group tensor Q. That's the base. And you get so this is actually a parameter space for the deformations of the Bukai category symplectic manifold. And now we have this really remarkable theorem which says that if you take a smooth projective variety, you blow it up in something of I this 2, which is smooth, then the base of the Frobenius manifold actually splits. As we know, the homology of the blow splits, so it's the same splitting, just you need to put the estimate to the correct opposites in there. And then we have an isomorphism of these A model F bundles. The A model F bundle for the blob breaks into external direct sum of the A model F bundle for the original X and n-1 copies of the A model F bundle for the center of the blob. And you need to choose your points where these germs are taken slightly carefully, but there is always such an isomorphism. So the real content of this theorem is a result of Iritani, who proved that in the formal case. And again, for us, it's needed in the analytic context, so we have to actually check that it makes sense analytically, which turned out to be surprisingly delicate, but not very difficult. Okay, so for an F bundle, just general wave bundle, we had this spectral decomposition theorem, which broke it under according to the spectrum of this extra symmetry kappa. There is also this blow-up decomposition theorem, which works for the A model wave bundle of a variety. They're compatible. So when you write down the formulas for the decomposition, you see that the pieces in the spectrum, and they're compatible from first principles too. The pieces in the spectral decomposition of the A model wave bundle, they arrange themselves as pieces inside the blow-up decomposition. So that tells you that the pieces in the spectral decomposition can be used as blow-up invariants. And so the idea is keep track of those pieces together with their natural symmetries and use that as invariants for rational maps or invariants for obstructions to rationality. Okay, so I need to talk about the symmetries and the symmetries. So one part, as I said, of this that's somewhat confusing is that there are too many Koch structures in the picture. So there are these non-commutative Koch structures that give you the pieces, give you the spectral decomposition. There are also usual Koch structures because we're dealing with homogeneous smooth projective varieties. And the key observation here is that these two types of Koch theories actually commute. So if you keep track of both of them at the same time, you get really interesting invariants. So to say in what sense they commute, we have to talk about the symmetries. So take the usual Manford-Tate group. So it's the Galois group of the category of pure polarizable Q-Koch structures. It has a character and a co-character. So the character is just the action of the Tate group on the Tate motif on the second homology of Q1. And the co-character is given by the Koch-shaped Koch gradient. So once you fix the weights, it will be just the Koch gradient. And so the group that we're interested in, because we're dealing with Z2 graded guys, so you really need to model by the action of the Tate Koch structure. So that's why you need to take the kernel of pi. So you take the kernel of pi. So it contains a copy of GM, which corresponds to the Koch gradient, and in particular contains one evolution, central evolution, which is image minus, which exactly gives you the even and odd gradient. So this is going to be our symmetry data, this group Koch, which is what these are the Manford-Tate group that acts trivial on the Tate motif, plus this extra evolution. And it's a pro-reductive group. It's the Galois group of the category of pure polarizable Z2 graded Koch structures. And the evolution grades the cohomologies into an even and an odd. So you lose the Z gradient of the cohomology, but you keep the Z2. Okay, so now I'm gonna just for concreteness, I'm gonna take this K to be the filter Crisot series in one variable over Q bar, and take the K analytic A model F bundle of a projective manifold. So the base now is given by full homology, an open politics in the full homology. Now the Q bar points of this Manford-Tate group of Z2 graded Koch structures, they act on this picture by analytical automorphisms. And the fixed points are some purely even K analytic closed submanifold. So this is what we get by intersecting with the lowest Koch. And yeah, that's what they say. It's an admissible open inside the law. And so this operator couple, this extra symmetry, which was the multiplication with the Euler vector field, it gives you an endomorphism of the bundle H0. Particularly, you can restrict the bundle H0 to this closed locus approach classes, and it gives you an endomorphism of that. So you can take the spectral cover corresponding to that endomorphism. Just the subvariety, the analytic subvariety given by the determinant of lambda minus K cover. So that spectral cover will be very nasty. And you see general highly non-reduced. So the first step is to reduce it. Look at the reduced spectrum. And then you do exactly the opposite of what Milton did in the previous talk. You throw away the screen. You take the branch divisor of the spectral cover and you remove it. And then you look at the pre-image of the open complement of the branch divisor into the reduced spectral cover. So you're losing a lot of information. Ludwig actually showed you that you are indeed losing information, but you, at the end of the day, you will get some invariant. So you get this unramified cover of a big open set in the locus approach, which is some remnant of the actual spectral cover. By the way, it may be a little bit a point of confusion, so let me just make this comment. This is the spectral cover of the symmetry of the endomorphism cover. It's not the spectral cover of the Higgs field we had before. The Higgs field also has a spectral cover, and that spectral cover is very important in this picture. It actually essentially defines the motion. Its properties, geometric properties define the motion of that bundle. But this is a different spectral cover. It's a spectral cover of the endomorphism. Okay, so you get this unramified cover, and the spectral decomposition theorem tells you that for a rigid point in the base of the cover, you can look at the germ of the bundle, the A-modular bundle that we started with in order to define the cover, and it splits into an external sum of germs. Now the germs are labeled by the connected components. And the whole splitting is equivariant with respect to the action of the one state. And I didn't say that, but the F bundle that we constructed from a symplectic manifold was actually maximal, and these guys are automatically maximal. Now they have some really great properties. So anyway, from the Gromf-Witten theory, not somehow so far, the really essential information we extracted was this set of connected components of that spectral cover. The spectral cover was defined in terms of the Gromf-Witten theory, and the set of connected components depends on the Gromf-Witten theory. And yeah, it has many great properties. Each of the summands is atomic, meaning that the operator kappa has a single eigenvalue. That summand. So its maximum, it has its own operator kappa, and that operator kappa has a single eigenvalue. Each summand is equivariant with respect to the action of the Mantel Tate group, and that's great because now you can look at the action of the Mantel Tate group on the fiber at the close point in the germ. It's a finite dimensional representation, it's a pro-reductive group, so it is covered by extension of scalars from Q bar to K of some Q bar representation, linear representation. And because these guys are defined up to analytic continuation, but continuous parameter, representation reductive groups don't have continuous parameters. So this E lambda actually is optoisomorphism is uniquely defined by one. And the Bohr theorem, and there is some version of the Lerach-Hish theorem which I didn't mention, which is the decomposition for projective bundles for F bundles. They imply that this decomposition into atomic pieces is actually compatible both with dwarfs and projective bundles. So this gives you this notion of an atom now. You say that the local atoms of a variety are just the connected components of that spectral cover. And the set of Koch atoms for all varieties is gotten by taking the set of atoms for varieties, modulo automorphisms, the joint union of those, and then model by an equivalence relations, which is generated by the equivalence relation that you get for the joint unions of varieties, for dwarfs with smooth centers, and for projective. So that gives you a big set for all smooth projective varieties of these atoms that appear in this decomposition that comes from non-cognitive force theory for these bundles, depending on the ground fluid. Now, how do you use it? So every Koch atom came by this construction with a finite dimensional Q-bar linear representation of the Pantev group. And it really, autoisomorphism depends only on the atom. And then you get numerical invariance. So for every Koch atom, you get actually the dimension of the locus of Koch class, which is just the eigenvalue 0 case in the alpha. And you get the polynomial. It's a Laurent polynomial, and it just counts the dimension of the other eigenspaces for the gradient group, for the Q bar, invertible elements in Q bar, which sit inside the model. But now, because we're just doing the Koch-shot grading, so this is not a reciprocal polynomial, right? So if this representation was really a Q representation, was a base change from a Q representation, then this will be literally a Q pure Koch structure because base change is not very good. And the polynomial will be reciprocal because this is the P minus Q gradient. But these guys are not reciprocal because there is no reason for these pieces to be base change from Q constant. They are just representations of the Pantev group over Q bar. But you do have this invariance, so you get a dimension of Koch classes and this Koch polynomial corresponding to Koch. And so here are some properties. I think Ludmil mentioned the first one. If you have a smooth projective variety with a net canonical class, then these atoms of X, the local atoms of the variety, they have a single atom. This spectral cover is connected. So that atom theory only gives you a breaking when the canonical class is not there. The other thing that you get essentially for free from the maximality condition and from the fact that these are coming with Venus products or quantum products is that for every Koch atom, the dimension of the locus of Koch classes is at least 1. And you get a non-rationality criterion which mimics the Clarence-Griffiths criterion, which says that if you have a variety of dimension at least 2, you look at its atoms, look at how the homology breaks into these representations of the Pantev group. Then, if you have an atom that does not appear in the atomic content of a variety of dimension, at least 2 less, then X cannot be option. Because in the Bohr, all those guys should be. And when you're starting with the projective space, all the atoms are just Bohr. So that's the non-rationality criterion. And you can actually apply it to a few cases by itself, not that many, but at least it gives you the non-rationality of a very general QE. So let me try to explain how it works. So you have this numerical invariance, the dimensions of the Hodge cycles and the Hodge polynomials, and you can distinguish the atoms that appear in the very general cubic from atoms that come from points, curves, or surfaces. So if you have any atom that comes from point or curves, then the coefficient in front of t square of the Hodge polynomial is 0. Because that's Hodge grading too. It's not infinite. If you have a minimal model of the surface, and the surface is not a general type or a K3 surface, then again, the coefficient of t square is 0. And if you take a minimal resolution of a minimal model of the surface of for which the canonical class is net, then then this thing has only one atom, and also the dimension of the Hodge class is at least big, because we are on a projective circle. We have at least the class for point, the class for the whole variety, and the class for the kind. So this is basically the complete behavior of this invariance for points, curves, and surfaces. And now when you look at the cubic, the four-dimensional cubic, using Poisson's Corelli theorem, you can see that for a very general four-dimensional cubic, the Hodge structure decomposes into a transcendental part which has Hodge type 121 and 5 algebraic pieces which are all the powers of K. So this is what the Young relations general. And using this and some fairly non-trivial Gromf-Witten theory, you can actually compute the atoms, or at least limit the atoms. In fact, you can compute them, but in fact, for the non-rationality, you need very little. You don't need to. So it all boils down to a classical theorem of Giventhal, which is celebrating Lefschetz. It's actually the quantum version of the Lefschetz hypermethylation for projective spaces. And when you do it for P5, you can use Giventhal's calculation and well, somewhere it's not completely obvious, but you need to work a little bit. But you can find a special point, same way Giventhal finds a special point in the logs of Hodge classes, so that when you Hodge classes, so it's going to be a point that really corresponds to the hyperplane class and all the other 0. And if you look at the operator kappa, you can compute its eigenvalues. Its eigenvalues are 0 and 9 times, which is 4 eigenvalues, which are 3 are rescalings of the third plus unity and 0. And each of these scaled third roots of unity has a single Hodge class eigenvalue. In fact, you know, when you dig deep in this Giventhal calculation, you can compute the dimension of the eigenspaces, the generalized eigenspaces for the quantum multiplication by the canonical class, all at this special point on all the algebraic classes. And so it's a 5-dimensional space of algebraic classes, and you get 1 2-dimensional generalized eigenspace for eigenvalue 0 and 3 1-dimensional. So the atomic content of X actually consists of 3 one-dimensional Koch atoms and 1 24-dimensional values here. As I said, you can compute it, and this is what you get. Oops. But you don't even need that. But let me do the argument this way. Already, you know, just the statement of the algebraic classes gives you everything for the non-rationality, but let me just do the statement this way. So you have these 3 one-dimensional atoms that look like atoms at point, and this 24-dimensional atom, which has 2 algebraic classes and 22 personalities. So that cannot come. Its coefficient in front of P square is 1, but the dimension of the Hodge classes is 2, and that cannot come from any. So that tells you that the theory is not rational. Do we do 50 minutes or an hour? Okay. So I can tell you a little bit about what Ludwig was mentioning about the cancer. So you can refine this notion of a Koch atom in various ways. So as I said, the theory up to here it's good. It gives you, I mean, there are a few other birational statements or non-birationality statements that you can get from it, but it exhausts its area of applicability very quickly. So if you want to get more powerful birational invariance, you need to you know, just the very naive definition of Koch atoms is not quite good. So I need to refine it, and you can basically refine it in 3 different ways. One is a pairing, which is going to be like Euler pairing on the category or chi pairing on more space. Other integral structure, and in this symplectic geometry work, that's something quite non-trivial because there is this, remember, there was this compatibility with the Stokes data, and that requires the usual integral structure to be corrected by an endomorphism, which is given by a gamma class. Special characteristic class depending on the gamma function. Actually, there is a third way which I didn't mention because it's not going to come in this particular set of applications, but Ludwig mentioned it and he had applications about it. We can add a second. We can add a duality. So any one of these 3 enhancements will give you something slightly better than the usual function. So the spectral decomposition of these bundles is compatible with the refinements. The Bloch decomposition is compatible with the refinements, certainly with the pairing and the duality refinements. The integral structure refinement we haven't quite proven it yet, and it's really tricky because we're doing these things analytically. Also, we need the spectral covers and the topology, but the real correspondence is not well developed over so you need to do really like very ad hoc constructions, but I think we're getting there. In fact, you can check it for surfaces, which is all we need in this set of examples. And so you get, again, you know, that the refined atoms give you obstructions to rationality in the same exact way, right? And you get interesting non-rationality results for quadric expectations. So this is the example that you mentioned. If you take now not a general cubic fourfold, but cubic fourfold containing plane, then projecting from that plane gives you a vibration by quadric surfaces on Y, a rational vibration by quadric surfaces. This birational vibration gives you some interesting atom. So the vibration gives rise to a double cover of the base of the net quadrix, which is the K3 surface. And then you have a universal ruling over that K3 surface, which is a Brouwer-Severi variety. And so you get the two torsion jerk on that K3 surface. And Kuznetsov has shown that this derived category sheaves of the two torsion jerk is a semi-orthogonal summand of the derived category of X, in particular homology of the twisted sheaves. It's a semi-orthogonal summand in the Hopf structure of X. He also checked that the numerical K-cube of this category of twisted sheaves is not isomorphic to the numerical K-cube of any smooth projective variety. And so the category cannot be equivalent to the category of any. Once you feed that into the formalism of enhanced atoms, you get that this alpha twisted core structure is a refined atom, refined with the pairing and the equilibrium structure, and the general cubic fourfold with the equilibrium. So again, the genericity is not relation genericity. You have one extra cycle, but you don't have any. And there is a similar thing with the intersection of three quadrics in P7. So I'm not going to go into details because Ron is going to talk about it on Thursday. If you have a general intersection of three quadrics in P7, you can choose a line in that intersection. Then some incidence correspondence related to that line gives you a quadric surface vibration birational on X. And again, you get the jerk, but now it's over a surface of general time. Double cover P2 branch along and it's two torsions still. And again, Kuznetsov's quadric bundle theorem tells you that this is a semi-orthogonal summand of the derived category of X. And then Ron will show you how you can check that the numerical K-theory of this jerk now is not the numerical K-theory of any smooth surface, which in particular implies that it's not, the category is not equivalent to the derived category of any smooth surface. And that gives you new proof of a theorem of Kasset, Pirotka, and Chinkel, a non-rationality theorem for the intersection of three quadrics, where they use the Gauss homology of the degeneration to prove it, which says that, again, the same statement, that this refined atom and that atom cannot come from a surface, so this thing cannot be rational. So just proof of concept that the machinery actually gives you good invariance. Okay, I'll stop here.